At first glance, the AI chip industry looks simple. Nvidia makes the chips, AMD is trying to catch it, and every few months, a startup claims it has built something 10 times faster. But that picture is wrong. Nvidia does not really sell a chip. It sells a complete computing system, processors, memory, networking, software, racks, and access through every major cloud. And the companies fighting that system are not all fighting the same war. AMD is trying to build another flexible general-purpose AI platform. Google and Amazon design private chips so they can stop buying quite so many GPUs. Companies like Cerebras and Groq rebuild the machine around particular bottlenecks, and Etched and Taalas go further still, sacrificing flexibility to make specific AI workloads dramatically more efficient. And underneath all of them are companies such as TSMC, Broadcom, and the manufacturers of the high bandwidth memory, companies that win regardless of whose name appears on the final processor. So there's no single AI chip race. Training is one war, inference is a completely different one. And then there are the fights over memory, over the wiring that binds thousands of processors into one computer, over the software everybody has to write against, and finally over who can manufacture enough hardware for any of it to matter. And that is why several companies can all claim to have built the fastest AI chip, and why some of those claims can be true. One chip may respond fastest to a single user, another serves thousands of people more cheaply, a third can train a frontier model, while a fourth run a particular model at extraordinary speed and cannot run the model invented next year. This video is a map of that entire industry. We're going to follow one AI answer through the machine, identify where it becomes slow and expensive, and then examine the radically different ways companies are trying to fix it. By the end, you understand why GPUs won, where Nvidia is vulnerable, which challengers are genuinely different, why promising chip startups keep dying, and why the company that benefit the most from Nvidia losing a sale may not be another chip brand at all. If you are interested in getting my videos in advance, please consider joining the membership. Members can also propose my next research topics. Research tier members can also download infographics from my videos. And this is for educational purposes, not financial advice. One AI model can feel mysterious, but the work inside the chip is surprisingly repetitive. The model contains an enormous collection of learned numbers called weights. Those numbers encode patterns learned through training. When you send the model a prompt, the machine repeatedly combines your input with those weights using multiplication and addition, not once, billions or trillions of times. Huge number of these calculations can happen in parallel. So instead of giving the job to a few extremely powerful CPU cores, AI systems use processors containing enormous amounts of parallel arithmetic. A CPU is built for unpredictable work. Operating systems, application logic, branches, and decisions. It has a smaller number of sophisticated cores that can each do different things. A GPU uses many cores, simpler workers, to apply similar operations across large collection of data. Calling a GPU general purpose requires a qualification. Compared with a CPU, a GPU is specialized for parallel numeric work. But compared with a chip built for only transformers or only one particular model, a GPU is extremely flexible. It can train a model, it can serve a model, it can run transformers, image generators, scientific simulations, and whatever architecture researchers invent next. That flexibility is one reason GPUs became the default platform for AI. But doing the arithmetic is only half the job. The processor has to retrieve it from memory. Picture a workshop. The arithmetic units are workers standing at workbenches. The weights are parts. A small number of parts can be stored on shelves immediately beside each worker, in very fast memory called SRAM. But an AI model contains far too many weights to keep them all there. Most might be stored in larger memory beside the processor. Modern AI accelerators commonly use high bandwidth memory, or HBM. Stacks of memory positioned close to the processor and connected through an extremely wide interface. HBM is a warehouse attached to the workshop. It is fast by memory standards, but accessing it still takes time and energy. Reaching further away into ordinary system memory or another processor costs even more. And this gives us the most important physical idea in the video. Moving data can cost far more than calculating with data that is already nearby. In a classical study of computing energy, retrieving data from external memory can consume hundreds of times more energy than a basic arithmetic operation. The exact ratio changes with the manufacturing process and the type of operation, but the underlying problem remains. Supplying the workers is expensive. Now watch what happens to your prompt. An AI response has two main phases. The first is called prefill. During prefill, the model processes the prompt you supplied. Many prompt tokens can be handled in parallel, creating a large burst of matrix computation. Longer prompts, uploaded documents, and large agent memories make this phase more demanding. Prefill is one reason there may be a pause before the first word appears. The second phase is called decode. During decode, the model produces the answer one token at a time. A token is a small unit of text, sometimes a word, sometimes part of one. Each new token depends on the sequence that came before it. So one user's answer cannot simply generate every future token simultaneously. For each new token, the machine passes through the model's layer again. It repeatedly streams enormous amount of weight data through the processor. During prefill, the machine often has a great deal of arithmetic to perform on each collection of weights. During decode, it may perform less arithmetic before it needs another large delivery from memory. That is why decode is frequently limited by memory bandwidth, not how much memory exists, but how quickly it can deliver data. The workshop has plenty of workers. The loading dock cannot feed them quickly enough. There's another growing consumer of memory, the KV cache. You can think of it as the model's working notes about a conversation. It stores information derived from previous tokens, so the model does not need to recompute everything from the beginning for every new token. Those nodes grow as the conversation becomes longer. They also multiply as the service handles more users simultaneously. So memory has two separate jobs. First, capacity, holding the model and working nodes. And second, bandwidth, delivering that information quickly enough. A machine can have enough room for a model, but still deliver its weight too slowly. Or it can have enormous bandwidth, but too little capacity to hold a large model efficiently. And one processor is rarely the complete system. Large models are divided across many processors. Those processors must exchange intermediate results rapidly enough to behave like one machine. That wiring is called the interconnect. If it is slow, processors wait for one another. A chip can therefore be faster in isolation and still create a slower system. You can win at the workbench, but lose across the workshop. Already we can see 3 different places a challenger might attack. Build faster workers, keep the parts closer, or connect the buildings more efficiently. But Nvidia's advantage comes from doing all 3, and then surrounding them with something even harder to benchmark. The familiar version of Nvidia's history is a quick story. It starts somewhere unexpected. The company at the center of the AI economy is the same company that makes the graphic cards in a gaming PC. Graphics processors were created to shade large numbers of pixels in parallel. Neural networks happen to require a similar pattern. Enormous amount of repeated arithmetic across arrays of numbers. Nvidia recognized that opportunity early. CUDA made its processor programmable for work beyond graphics. Tensor cores later added circuitry, specifically optimized for the matrix calculation used in AI. Start with the processor. Around it sits high bandwidth memory, then a proprietary high-speed interconnect that lets many processors inside a rack cooperate as one machine. Networking joins those racks into clusters of thousands. Software turns models into efficient instructions, coordinates communications, and managed inference. A complete rack supplies power, cooling, and reliability. Behind all of it, a supply chain delivers wafers, advanced packaging, memory, and networking components in enormous volume. And distribution put a finished system in every major cloud, with trained engineers and support attached. That's what a customer is buying, not merely a chip, a functioning industrial system. And now the numbers, because this is where most coverage of the AI chip war loses grip on scale. In its most recently completed fiscal year, Nvidia reported $215.9 billion of revenue, up 66%. In its most recently reported quarter, data center revenue alone was $75.2 billion, up 92% year over year, on total revenue of $81.6 billion. Gross margin runs around 75%. Two details inside those numbers matter even more than the headline. First, the networking line. In the fourth quarter of last fiscal year, Nvidia's networking revenue hit $11 billion, up 263%. That isn't a chip business. That's Nvidia setting the road between the buildings, and it's growing faster than the processors. Nvidia has guided the current quarter to roughly $91 billion. If that lands, Nvidia will be generating more revenue in one quarter than most semiconductor companies generate in a decade. Estimates of its share of the data center AI accelerators cluster around 80%. So Nvidia is a giant machine that is still expanding at enormous scale. But here's the part that matters strategically. Several companies have built accelerators that beat Nvidia processor on a specific job. It didn't matter, because the customer was never buying a processor. Switching away from that system creates real work. Software may need rewriting or retuning. Models must be rechecked to confirm output quality hasn't shifted. Engineers must learn new tools, and large deployments take on operational risk. But this isn't an unbreakable wall. Google has run major models on its own TPU for years. Amazon and Anthropic used Trainium at enormous scale. AMD software has improved substantially. When another platform offers a large enough economic advantage, customers accept substantial migration work. Here's the right way to think about Nvidia's moat. Nvidia's stack reads the advantage a challenger must demonstrate. Before switching makes sense, it doesn't make switching impossible. A switching cost is a threshold, not a wall. A 10% advantage disappears after software integration costs. A genuine 2x advantage on important production workload gets serious attention. A verified 10x improvement in quality-adjusted tokens per dollar could force the industry to reorganize around it. But 10 times better must describe the whole useful result, not one convenient number. AMD's answer is the broadest possible one. Training, prefill, decode, all of it, on the same silicon, the same way Nvidia does. AMD is the only company in this video attempting to compete across Nvidia's entire territory, rather than carving out a piece of it. So who is this chip actually for? A company running a large mixed fleet, training frontier models one week, serving them the next. They also want a supplier other than Nvidia. Anthropic will train and serve cloud on it. Meta will run ranking and generative workloads on it. That breadth is the entire pitch. AMD is the clearest merchant alternative to Nvidia. Build another programmable accelerator, capable of training and inference, add large amounts of high bandwidth memory, connect many accelerators into one rack, supply processors, networking and software around them. In other words, compete with Nvidia on Nvidia's broadest territory. This is difficult because AMD cannot win by producing an impressive processor alone. But over the last 12 months, something changed. In October 2025, OpenAI committed to deploy 6 gigawatts of AMD accelerators across multiple generations, and AMD issued OpenAI warrants for up to 160 million AMD shares, priced at a cent each, vesting against deployment milestones. In February this year, Meta signed an equivalent arrangement, another 6 gigawatts, reported at around $60 billion over 5 years, with its own 160 million share warrant. Then on July 22nd of this year, Anthropic, a company that had been running on Nvidia, Google TPUs, and Amazon Trainium, agreed to deploy up to 2 gigawatts of AMD's MI450 series accelerators in AMD's Helios rack, beginning in the first half of 2027. AMD will invest up to $5 billion into Anthropic, as deployment milestones are met. And the two companies signed a separate engineering agreement to tune AMD's ROCm software specifically for cloud, and Microsoft Azure and Oracle as disclosed Helios customers. And AMD's announced deployment pipelines reached roughly 20 gigawatts. Today, AMD's data center segment runs about $5.8 billion a quarter, growing 57%, against NVIDIA's $75.2 billion. That is roughly $1 for every 13. Now for the question everyone actually wants answers. How good is the silicon? Is it 90% as good as NVIDIA, equal, or better? Here are the two flagship chips, side by side. At memory capacity, AMD wins decisively, 433 gigawatts of HBM4 against Rubin's 288, 50% more. At memory bandwidth, they are close enough to argue about. AMD published up to 23.3 terabytes per second, NVIDIA published 22. On compute, it flips. Rubin claims 50 petaflops of 4-bit inference. The MI455X claims 40. So on that highlight number, AMD is at roughly 80% of NVIDIA. But move to 8-bit, and it reverse. AMD is 20 petaflops against Rubin's 17.5. So now AMD is 14% more. And that is the honest answer to how much better or worse. There isn't one, depending on which row of the table you pick. The numbers can also get slippery, because those 4-bit numbers use different numerical formats. AMD's own summary claim is 15 to 25% higher training performance than very Rubin, and roughly 30% in performance per dollar. But here's another detail I find useful, and it came from AMD itself. Ahead of the launch, AMD's vice president for AI software told press that in real-world testing, the MI455X reached 20 petaflops of 4-bit performance, exactly half of its 40 petaflop peak. It's the normal condition of all AI silicon, including NVIDIA's. The peak number tells you how high the roofline is. It tells you nothing about whether you can reach it. So the more meaningful question isn't whose roofline is higher, it's who got closer to their own. And that's decided by software. I want to be precise about what those AMD contracts represent, because they are easy to misread. Nobody is leaving Nvidia. Meta committed to 6 gigawatts of AMD accelerators, rented Google's TPUs, and separately committed to millions of Nvidia Blackwell and Rubin GPUs, all within a few months. Anthropic runs workloads on Nvidia, on Google TPUs, on Amazon Trainium, and now on AMD. These aren't migrations, they're portfolios. The largest supplier in the world have concluded that, depending on one supplier for the most strategically important input in their industry is itself a risk, and they're willing to absorb real engineering costs to fix that. AMD's opportunity isn't that its chip is better, it's that being the credible second source is a valuable position, even when you are second. But first, consider the companies with advantage AMD doesn't possess. They're both the chip designer and the chip's largest customer. Now we'll need to talk about the hyperscalers themselves building chips. These chips are not Nvidia chips that can do a variety of jobs. Instead, they are built around workloads in their own needs. Even the naming tells you how deliberately this company think about the split. Amazon runs 2 separate lines, Trainium for training, Inferentia for inference. Google's newest TPU generation, Ironwood, was explicitly positioned for what the company called the age of inference, while earlier generations trained Gemini. The job split we spent chapter 1 on isn't an academic distinction to these companies, it's a product roadmap. So who are these chips for? Themselves first. A TPU is designed around the specific shape of Google's workloads, ranking billions of YouTube recommendations, running search, training and serving Gemini. Trainium is designed around what Amazon's biggest AI customer needs, which in practice means training and serving cloud. These are not general-purpose products that happen to be sold internally. They are shaped, generation by generation, around a workload the designer can see in advance because they own it. That is the whole advantage. Imagine your company expects to spend tens of billions of dollars buying the same type of machine. At some point, designing your own machine begins to look rational. Google doesn't need to make a chip that every research lab loves. It needs a chip that runs Google's enormous recurring workloads efficiently. It already owns the data centers, controlling much of the software, and has internal demand waiting before the first processor ships. That changed the economics completely. Google's Tensor processing unit is more focused on neural network mathematics than GPU, while remaining programmable enough to train and serve major models. And you have been using TPU for years without knowing it. When Google Photos find every picture of your dog, when Translate handle a menu through your camera, when Search understand a badly worded question, when YouTube decide what to autoplay next, that is TPU silicon. Gemini was trained on it. Waymo trained its self-driving models on it, in Google's data centers, before those models ever reach a car. That is a quiet fact underneath this entire chapter. The most successful challenge to NVIDIA's architecture has been running inside products you use every week, for the better part of a decade. Its 7th generation Ironwood scales to pods of 9,260 chips, sharing 1.77 terabytes of high bandwidth memory. Google's own Gemini models run on TPUs, and outside customers can reach them through Google Cloud. And here is where this attack becomes real, because now other people also want to use it. Anthropic agreed to a deal with Google worth up to $40 billion, covering 5 gigawatts of TPU capacity over 5 years, and access to as many as 1 million Ironwood chips, roughly 1 gigawatt arriving in 2026, scaling past 3 gigawatts in 2027 through Broadcom. In February of this year, according to reporting by The Information, Meta signed a multi-year, multi-billion-dollar agreement to rent Google TPUs for training and running models, while separately committing to millions of Nvidia GPUs and that 6 gigawatt AMD deal. Salesforce, Midjourney, and Replit are running production workloads on Ironwood. Google has said publicly it believes it can capture up to 10% of Nvidia's data center revenue in the coming years. The most revealing detail, though, is internal. Bloomberg reported this spring that Google's own researchers, including teams inside DeepMind, are now queuing for TPU capacity because so much of it has been sold to Anthropic and Meta. Google industrialized its chip so successfully that it ran short for itself. Amazon followed a similar logic with Trainium and Inferentia. It controls the largest cloud platform, operates the data centers, and can price aggressively to move customers onto its own silicon. Anthropic provides the anchor workload. Project Rainier came online with roughly 500,000 Trainium 2 chips, and Anthropic now runs more than 1 million of them. Trainium 3, Amazon's first 3nm accelerator ships in ultra servers of up to 144 chips. Every internal TPU or Trainium deployment represents a workload that might otherwise have required Nvidia hardware. This competition is easy to underestimate because much of it never appears in merchant market tables. Google isn't trying to place TPU in electronic stores. Amazon isn't trying to convince every university lab to abandon CUDA. They are reducing dependency inside their own walls. That's why custom silicon may be the largest threat to Nvidia's economics, even if no independent startup ever becomes the next Nvidia. And the model is spreading. Meta deploys MTIA, roughly a $35 billion program with Broadcom, with an initial commitment above 1 GW, against 2026 capital spending of roughly $115 to $135 billion. If you ever wonder what decides which reel plays next, or which post sits at the top of your feed, that ranking work is exactly what MTIA was built for. It's probably the AI chip that touches the most human being per day, and almost nobody outside the industry knows its name. Microsoft launched Maya 200 in January, 3nm, 216 GB of HBM, deployed in 72-chip Ethernet racks of its own services. OpenAI is working with Broadcom on a 10 GW custom accelerator program, with its first generation chip slated for volume deployment in 2027. And this month, a wrinkle appeared that tells you something about what all of this is heading. Reports from the semiconductor research firm SemiAnalysis suggest Google is working with AMD on one variant of its 10th generation TPU. Not a conventional accelerator, Google has 9th generation of its own expertise there, and a supply agreement with Broadcom running through at least 2031. What Google appears to want from AMD is different. General-purpose CPU cores placed directly inside the accelerator package, along with AMD's advanced 3D packaging. Why would you put a CPU inside AI chip? Because of what AI workloads are becoming. Reinforcement learning and agentic systems, models that take actions, called tools, and evaluate results, spend far more time on ordinary general-purpose computing than a straightforward chatbot does. Putting the CPU on the same package as the accelerator cut the distance between the two, which is the data movement lesson again, arriving from a new direction. Although this is just analyst reporting rather than announcement from either company, but treat it as a signal. The merchant challenger from our last section may be supplying components for the captive challenger in this one. The categories on our map are starting to bleed into each other, and we'll come back to that, because it turned out to be the direction the whole industry is moving. But custom silicon also has limits. It makes sense when the buyer is enormous, has predictable demand, and can support a large engineering organization. A smaller company can't casually spend years designing silicon, reserve advanced manufacturing capacity, create a compiler, build servers, and hope its workloads stay unchanged. And even hyperscalers keep buying Nvidia systems. Why? Because internal chips and Nvidia chips serve different needs. Custom silicon works well for stable workloads with enormous volume, while Nvidia's remains valuable for researchers exploring new ideas, for customers demanding compatibility, and for workloads that change faster than hardware can be redesigned. This isn't necessarily replacement, it's segmentation. Its first phase of AI rewarded generality, because the models change constantly. As inference grows, the same models may execute billions of times. Repetition creates economic opportunity for specialization. So here's the trade-off. When it changes, the customer relationship rather than the architecture. The chip is the means. The goal is to stop writing the check. What this company gains is guaranteed internal demand before the first chip exists, total control of the software stack, and no need to persuade anyone. The buyer and designer are the same company. What they give up is the option of selling it. Custom silicon requires engineering depth almost no company possesses, and it only pays back on workloads stable enough to justify a multi-year design cycle, which is precisely why all of these companies keep buying Nvidia alongside it. Google and Amazon specialize at the workload and platform level, but this next company attack a different problem. Why divide the processor into chips at all? Cerebras is technically capable of the full range. It sells systems for training and for scientific computing, and those are real businesses. But look at where the money went. The contract that transformed this company was for inference capacity, and the metric it's famous for, tokens per second delivered to one user, is a decode metric. On paper, it's a general machine. In the market, it has become a decode specialist. So what is it actually for? Applications where a person is waiting. A reasoning model that thinks for 30 seconds before answering becomes a very different product if it thinks for 3. Coding assistants, research agents, anywhere where the delay is the thing users complain about. Cerebras also sell into scientific computing and simulation, where its enormous on-wafer bandwidth suits problems that have nothing to do with language model at all. The physical idea behind all of this is, instead of cutting a silicon wafer into hundreds of separate chips, Cerebras keeps almost the entire wafer intact and turn it into one enormous processor. It's called the wafer scale engine. Now, why does keeping the wafer intact help at all? The usual explanation is that the distance is shorter. That's true, and it's the smallest part of the story. Here's what's really going on. Inside the chip, the wires connecting one part to another are printed in the same manufacturing steps as the transistors themselves. They are nanometers apart. You can have millions of them running side by side, and each one is so small that pushing a little bit down it costs almost nothing. Now watch what happens when a signal has to leave that piece of silicon. It exists through a pad, then a solder bump, then a package, then a board. And those structures are physically gigantic, next to on-chip wiring, tens of microns apart, rather than nanometers, which means two things happen at once. First, the connection has to drive a much larger electrical load, so it burns far more energy per bit. On chip, moving a bit costs a fraction of a picojoule. Getting it off the package can cost 10 times that or worse. Second, and this is the real constraint, you can only fit a tiny fraction as many wires. Millions of connections inside the silicon become thousands leaving it. Engineers call this the beachfront problem. Your ability to move data in and out is limited by the edge of the chip. And the edge doesn't grow just because you added more compute inside. So Cerebras asks a direct question, what if we never leave? Its wafer scale engine keeps almost an entire wafer as one processor. Compute, memory, and communication spread across the whole surface, connected by wiring printed in the same lithography as the transistors. Millions of cheap connections instead of thousands of expensive ones. Which raises the obvious question, why doesn't everyone else do this? Because of how chips are printed, lithography works by projecting a pattern through a mask onto one small area at a time, then stepping across the wafer and repeating. There's a maximum size to each exposure, roughly 858 square millimeters, and normally you cannot draw a wire that crosses from one exposure into the next, because the machine physically moves between them. That limit is called the radical limit, and it's the reason a chip has a maximum size. So Cerebras' real achievement was not a design decision, it was a manufacturing one. Working with TSMC, they developed a process that stitches wiring across those boundaries, printing connections through the gaps between exposures, so separate fields become one continuous fabric. In workshop terms, everyone else builds separate buildings, and then argue about how to connect them. Cerebras got permission to build one floor with no walls. For years, Cerebras was the most interesting chip company with the least convincing customer list. In 2025, it did $110 million of revenue, up 76%, but 86% of that came from two related UAE entities, one customer essentially. Then in January of this year, OpenAI signed a multi-year agreement for 750 megawatt of Cerebras inference systems, valued at more than $20 billion, and lent Cerebras $1 billion in working capital to build the capacity. Amazon signed a partnership to bring Cerebras inference to AWS. In May, Cerebras went public, raising $6.4 billion in gross proceeds, the largest semiconductor IPO ever completed. So the customer concentration problem was solved, only to be replaced by a different one. Now a single customer named OpenAI anchors the story. Cerebras still had the strongest independent evidence of any specialist in this video. Outside benchmarking services have repeatedly measured it as the fastest per-user inference available on the models they support. Fastest at delivering tokens to one user on a supported model is a different question from cheapest at serving 10,000 users on any model you choose, because every bottleneck you eliminate creates another constraint. And here, the tree becomes very clean, because it's a mirror image of the one Nvidia made. Nvidia accepted the boundary and spent its engineering on advanced packaging, bounding memory stack as close to the compute die as physically possible. That buys capacity, 288 gigabytes of high bandwidth memory, sitting beside a single Rubin GPU. Cerebras refused the boundary and got extraordinary bandwidth, but only 44 gigabytes of memory on the entire wafer. And the wall returns eventually. One wafer is the limit. When the new chip CS4 puts 3 of them in a rack, those wafers talk to each other over conventional links, measured in terabits per second, not petabytes. Cerebras didn't eliminate the boundary problem. It bought itself a very large island. And the financial picture is generally mixed. Second quarter revenue reached $180 million, up 74% year over year, with cloud revenue nearly quadrupling, and it fell from $193 million the previous quarter. The company carries more than $25 billion of contracted revenue not yet delivered, and is still posting large losses. Contract revenue is a promise. Delivered revenue is a business. Cerebras has an enormous amount of the first and is still building the capacity to produce the second. So the accurate conclusion isn't that Cerebras solved the interconnect. It moved the boundary much further out and inherited new questions about memory capacity, manufacturing, power delivery, and deployment economics. That pattern will repeat throughout this video. A challenger removes one form of waste by accepting a different kind of risk. So here's the trade-off. What it changes is where boundaries sit. Instead of cutting the wafer into chips and rebuilding the connections out of solder and packaging, Cerebras keep the wiring in the same layer as the transistors. Millions of cheap connections instead of thousands of expensive ones. What a customer gains is per user latency that independent benchmarking had repeatedly confirmed on the models it supports, and on-wafer bandwidth no multi-chip system can approach. What a customer gives up is memory capacity, and a lot of it, 44 GB across the wafer, against 288 on a single competing GPU. Large models need external memory, power and cooling are demanding. There's no second manufacturing source, and the contracted revenue still has to become delivered revenue. Cerebras changed where the boundaries sit. Next company we're going to talk about, Groq, changed the way the work is scheduled, and then something remarkable happened to it. This is the narrowest job description we have seen so far, and it's narrow on purpose. Groq doesn't chain. It isn't built to chew through your prompt. It exists to do one thing, generate tokens, one after another, as fast as physically possible. Nvidia's own product design confirms the diagnosis. In its new rack, GPUs handle prefill, and Groq-derived chips handle decode. Even the company that bought the technology treated it as a one-job processor. So what is it for? Conversation essentially. A voice assistant that has to answer before the silence gets awkward. A coding agent that completes your line while you're still thinking. Any product that a human being is sitting there watching words appear, and where the difference between fast and instant changes how often they use it. That's a real and valuable category. It's simply not the same category as serving 10,000 batch requests at the lowest possible cost. To understand what Groq changed, we need to look at two kinds of memory inside every computer you have ever used. The first is SRAM, memory built directly into the silicon, alongside the transistor doing the math. It holds its value as long as the power is on, and reading from it is close to instant. The second is DRAM, which lives outside the compute die. On an AI accelerator, it takes the form of those high bandwidth memory stacks we have been discussing, slower to reach, but vastly larger. Why do we need both? Because of cost. An SRAM cell needs 6 transistors on expensive logic silicon. A DRAM cell is 1 transistor and a tiny capacitor, made on a cheaper process built purely for density. Bit for bit, SRAM takes something like 100 times the area. So the ratio on a normal AI chip is brutal. A few hundred megabytes of SRAM against a few hundred gigabytes of DRAM, roughly 1,000 to 1, which is why the weight lives in DRAM and can stream across as needed. In our workshop, SRAM is a workbench, DRAM is the warehouse. And here is what that warehouse costs you, beyond the bandwidth problem we already know about. DRAM is unpredictable. It's organized in rows, and before reading anything, the chip has to open a row. If your data sits in a row that's already opened, it comes back quickly. If it doesn't, the chip closes that row and opens another, several times slower. The same instruction takes a different amount of time, depending on what happened immediately before it. DRAM also leaks, each cell holding its bit as it changes that drains within milliseconds. So the chip keeps pausing to refresh itself, asks for data mid-refresh, and you wait. And you are never the only one asking. Thousands of operations share that memory system, so your request queues behind everybody else. Put those all together, and a single memory access might take 200 cycles, or 2,000. Nothing in the program decides which. Now a quick word about cycles. A chip has a clock ticking a couple billion times a second. One tick is 1 cycle, the smallest units of anything happening. And every cycle, something has to decide which of the chip's thousands of arithmetic units fire, on which numbers. That decision can be made in only 2 places, while the chip is running, or before it ever runs. A GPU decides while running, because it has no choice. It cannot know when data will arrive, so it carries dedicated hardware, whose entire job is watching what's ready this instant, and dispatching work accordingly. When one group of work stalls waiting for memory, the scheduler swaps in another, so the arithmetic units are not sitting idle. Written out, a GPU cycle looks something like this. Cycle 1, one group of work issues a multiply, while another requests memory. Cycle 2, the first group continues, the second is stalled. Cycle 3, still stalled, so the scheduler swaps in a third group, and then, at cycle 340, that data finally arrives, and the scheduler swaps the second group back in. Look at that number, 340. It wasn't designed. It's an outcome. Run the same program again, and it changes. And notice how many of those cycles are not doing arithmetic at all. They are dispatch decisions. The chip figuring out what's allowed to do next. That scheduling machinery is a real portion of expensive chip, and it produces no math. It exists purely to cope with the delay nobody can predict. So Groq deleted the warehouse. No DRAM at all. The waste leaving SRAM on the chip permanently. Two things follow. The bandwidth becomes extraordinary. Roughly 500 megabytes of SRAM per chip, running at about 100 terabytes per second, against 288 gigabytes of HBM at 22 on Nvidia's Rubin, hundreds of times less memory, moving several times faster. For decode, with re-read waits for every single token, that's close to the ideal shape. But every read now takes the same fixed number of cycles, always, no rows to open, no refresh, no queue, which unlocks the bigger idea. If timing is perfectly predictable, the compiler, the software that turns the model into instructions, can then plan the entire program in advance. Every operation, every data movement, scheduled down to the cycle, before the chip ever powers on. Cycle 1, the arithmetic units multiply. Cycle 2, results shift across, and the next values arrive. Cycle 3, they accumulate. Cycle 4, shift again. Every cycle accounted for. No stalls, no swaps, nothing waiting. And that isn't because Groq has fewer workers. It has thousands too. It's that a GPU needs spare work standing by, and Groq doesn't. Once the decisions are already made, the decision-making hardware has nothing left to do, so Groq removed it, and spent that silicon on arithmetic instead. And that's the actual invention, not faster memory. Remove the source of unpredictability, and all the machinery built to cope with unpredictability disappear with it. A busy intersection needs light, sensors, and a controller reacting to whatever shows up. But a railway needs none of that, because the timetable was written in advance. The timetable isn't actual work, it's what lets you skip building the traffic lights. But now there's a problem, and it's a serious one. Half a gigabyte per chip, $70 billion parameter model needs around 70 gigabytes. The model doesn't fit on one chip. It doesn't fit on 10. You need well over 100, each holding one slice, arranged in a pipeline. Your request traveling down the chain, which sounds fatal until you ask what actually crossed the wires between them. It's not the weights. Those never move. Each chip holds its slice permanently. What travels is your request, the intermediate result passing from layer to layer. And that is small, tens of kilobytes, against 70 gigabytes of weight. Groq didn't eliminate the boundary between chips. It changed what has to cross it. The real bill arrives as cost. Each individual chip is relatively cheap. Older manufacturing process, no expensive HBM, no advanced packaging to bond it, no scheduling hardware. But you need 100 of them, plus their power, cooling, rack space, and networking, to serve a model that fit on a single GPU. An inexpensive chip times 100 is not a cheap machine. And because it's a pipeline, it only works like a conveyor belt. Requests have to keep arriving, so every chip always has something in front of it. When the traffic thins out, most of those chips have nothing to do, while the bill stays the same. A half-empty Groq rack is very expensive indeed. That's why two apparently conflicting statements can both be true. Groq can deliver exceptional tokens per second to one user, while different architecture deliver better total tokens per dollar at large scale. Now the part of this story that tells you the most about the whole industry. In December 2025, Nvidia paid roughly $20 billion for Groq's assets and a technology license, and hired its founder across with much of the engineering team. It's the largest transaction in Nvidia's history. 3 months later, at its March developer conference, Nvidia announced the Groq 3 LPX, its first rack built around a non-GPU inference chip. A single LPX rack hosts 256 LPUs, providing 128 gigabytes of SRAM at 40 petabytes per second of aggregate bandwidth. and Nvidia's design is explicitly a division of labor. Rubin's GPU handle prefill, LPUs handle decode. Nvidia described the LPU as a decode model booster. Crucially, it confirms that no change to CUDA are required. Nvidia claims the LPX rack delivers up to 35 times higher inference throughput per megawatt than the Blackwell NVL72 for trillion parameter models, at 300 tokens per second and $45 per million tokens. So here's the trade-off. What it changes is unpredictability. Remove the external memory, and every operation takes the knowable amount of time, which lets the compiler schedule everything in advance, and lets the chip drop the hardware that exists to improvise. What a customer gains is token per second delivered to one user, and predictability. Latency you can actually promise someone. What a customer gives up is capacity, and therefore chip count. Half a gigabyte per chip means a large model needs hundreds of them. So an inexpensive chip becomes an expensive system, and the economics only work when the pipeline stays full. This is the one approach in the video where the architecture and the company had completely different outcomes. The architecture was validated at $20 billion. The independent business wasn't what survived. The specialist didn't destroy the generalist. Its idea became a component inside the generalist platform, and Groq's remaining independent business now competes against its own technology, sold by Nvidia. But several companies are pushing specialization much further. Notice something about all three companies in this section. Every one of them has crossed the same line. None of them train. It's a trade they chose. Training demands flexibility because the recipe changes constantly. Inference is the same computation over and over, billions of times, and repetition is what makes specialization pay. The three companies here simply disagree about how far to take it, and each is aimed at a different customer. D-Matrix sell a card that slides into an ordinary server for operators that want more interactive throughput per watt without rebuilding their data center. Etched target whoever serves transformer models at enormous volume, an inference provider running the same model class millions of times a day. Taalas aim at the narrowest target of all, one specific popular stable model, served so many times that burning it permanently into silicon becomes the cheapest way to run it. Read that as a progression. The broader the customer, the more flexible the chip. The narrower the customer, the more the hardware can be stripped away. A GPU must be ready for models and algorithms that didn't exist when the processor was designed. That requires programmable arithmetic, flexible data movement, scheduling logic, and broad software support. But if you know exactly what computation will run, why pay for all that flexibility? There's already a familiar version of this trade on the road. Tesla stopped buying general-purpose chips for its cars and designed its own, built to run its driving software, and nothing else. That chip will be useless in a data center, and the data center GPU will be impractical in a car. Nobody considers that a scandal. It's simply what happens when a workload becomes predictable enough and large enough to deserve its own silicon. The companies in this section are asking whether AI inference has now reached that point. There are several increasingly radical answers. D-Matrix, put the arithmetic inside the memory. Start where we just left off, because D-Matrix takes Groq's idea one step further. Remember what Groq did? It deleted external memory and kept the weight in SRAM on the chip. Enormous bandwidth. But look closely at what still happens on Groq chip. The weight sits in SRAM in one place, and the arithmetic unit sits somewhere else on the same die. When it's time to multiply, those numbers still have to travel across the chip into the compute hardware, and the results travel back. It's a short chip, far shorter than going out to HBM, but it's still a chip. And in decode, you make it for every weight, for every token, forever. D-Matrix asked, what if the weight didn't travel at all? Their approach is called digital in-memory computing. Instead of putting all the arithmetic in one region of the chip, they scatter hundreds of small pieces throughout the memory array. Every little block of SRAM gets its own multiplier accumulated hardware built directly alongside it. Now the weight doesn't cross the chips. It moves microns to a circuit sitting immediately beside its own storage. The activation is broadcast in. The math happens right there among the storage tiles, and only the answer comes out. HBM moved the memory beside the chip. Groq moved it onto the chip. D-Matrix moved the arithmetic into the memory. Each step attacked the same law from chapter 1, which is moving data costs more than computing on it, and each step shortened the distance a little further. And it matters most in decode, where the same weights are read again and again to produce one token at a time. One thing to be clear about, because it becomes important shortly, these weights can still be changed. This is ordinary rewritable memory, just with arithmetic built into it. Load a model, run it, unload it, load a different one, power the card down, and the weights disappear, exactly like the memory in your laptop. But hold that thought, because one company in a few minutes does not give you that option. Commercially, Matrix is the most conventional of the specialists, and that's deliberate. It sells 4 Corsair chips packaged on a card that slides into an ordinary server slot and costs tens of thousands of dollars, plug and play, rather than a new kind of computer. It built a full rack system with Arista, Broadcom, Supermicro. The chip is made on TSMC's 6nm node. The next generation Raptor targeted 4nm. Backers include Microsoft's venture arm, SK Hynix, and Marvell, at a valuation around $2 billion. Now we look at D-Matrix performance figures. Roughly 30,000 tokens per second on a 70 billion parameter model, with large claimed power advantages. Those are company claims, not independently verified. And the trade-off is one we have now met twice. Interleaving arithmetic into the memory array means the arithmetic occupies area that memory cells would otherwise use, so you get less SRAM per square millimeter than a pure memory design would. Large models still need many cards, and the advantage is strongest where the model and workload fit the architecture well. Etched make a different sacrifice, and its name created a misunderstanding I want to clear up immediately, because it matters for what comes next. Etched does not burn a model into silicon, it hardwired the architecture. Here's the difference. Every transformer, whatever its name, performs the same sequence of operations, project the input into queries, keys and values, compute attention, runs a feed-forward layer, repeat. That pattern is identical whether you are running GPT, Cloud, Llama, or DeepSeek. What differs between those models is only the numbers, the weights. So Etched built the pattern into the circuit, the data flow, the attention mechanism, the layer sequencing, fixing hardware, rather than expressed as instructions the general processor has to decode and schedule. The weights still load from memory, normally like any other chip, which is why one Etched chip can run many different transformer models, but cannot run something with a fundamentally different shape. And that's where the speed comes from. A GPU spends enormous silicon area on being ready for anything: instruction decoding, flexible scheduling, general purpose data path. If the sequence of operations is known in advance and built into the wiring, none of that is needed. Delete it, and the freed area becomes more arithmetic. So the analogy isn't a kitchen that makes only one hamburger. It's a kitchen that can cook any recipe you like, as long as it's a sandwich. For 4 years, Etched was a company with a thesis and no product. That changed on June 30th of this year, when it exited stealth mode with working first-generation silicon and more than $1 billion in signed customer contract before shipping a single production rack. Then the last 2 months happened. In July, it raised at a $10.3 billion valuation. On August 18th, it raised $700 million more at $21 billion valuation. In December, it had been worth $5 billion, 4 times in 8 months. And the round was led by Jane Street, the quantitative trading firm, which tested the hardware, bought it, took delivery of the first rack Etched has ever shipped to a customer, installed it in its own data center, and then led the financing. Etched newest description of the product has also shifted. It's no longer one chip. It's a system built from 2 custom pieces, a low-voltage chip designed for prefill, and a new shared memory and interconnect design for decode. A company founded to build one specialized processor now ships a machine organized around exactly the division of labor we established in Chapter 1. Etched has claimed roughly 500,000 tokens per second on a 17 billion parameter model from an 8-chip server, against roughly 25,000 for comparable H100 configuration. And as of this recording, there are still no independent third-party benchmarks and no public pricing. So the correct statement isn't Etched is 20 times faster than Nvidia. It's Etched claim a very large advantage on one workload class, now has one deployed customer who likely enough to invest, and still hasn't been independently measured. More importantly, its strength remains a strategic risk. What happens if future models rely heavily on different architecture, state spec models, new forms of mixture of express routing, diffusion-based language systems, or something not yet invented? A GPU can be reprogrammed, wiring cannot. Next is Taalas. Taalas pushed the argument as far as it can possibly go. Etched fixed the architecture and let you load any weight. Taalas fixed the architecture and the weights. The company described it with a striking phrase: the model is the computer. Why would that be so efficient? Because conventional inference spent its life retrieving billions of weights, so the weights are physically built into transistors. Most of that retrieval simply doesn't exist, and neither does the hardware that would have supported any other model. Mechanically, the chip split into two regions: a mask program fabric, hold the model's weights permanently, fixed at the moment of manufacture. A smaller SRAM region stores the KV cache and lightweight adaptations, and that part can change while running, with a narrow updatable layer on top. And let's be precise about what frozen means here, because it's the most restrictive job description in this entire video. The chip cannot train. It cannot be given a different model. It cannot even have its weights updated. Those are fixed during fabrication. The way words are fixed on a printed page. Here's a whole letter in one frame. A GPU fixes nothing. Everything is loadable. Etched fixed architecture. The weights stay loadable. Any transformer works. Taalas fixed architecture and the weights. Nothing is loadable. Everything a GPU does through software, the chip does through fabrication. According to Taalas' claim, it is dozens of times faster than Nvidia H200, and its own measurement put a B200 at around 350 tokens per second on the same model. Both are pre-user figures. Then, on August 6 of this year, AMD announced a definitive agreement to acquire Taalas, with the deal expected to close in the fourth quarter, subject to regulatory approval. AMD said it plans to integrate technology into system-level solutions alongside Instinct GPUs. Look at the pattern. Nvidia bought the leading deterministic inference company in December. AMD bought the leading model in silicon company in August, 8 months apart. Neither especially beat the incumbent. Both were absorbed by one. And notice what the Taalas acquisition actually proves. The memory bottleneck that makes inference expensive isn't a law of physics. It's a design choice. And design choices can be engineered away. The market is currently pricing that bottleneck as permanent. Conventional DRAM prices rose roughly 90% in a single quarter, and high bandwidth memory is effectively sold out for the year. If the bottleneck is a choice, that pricing is a bet. AMD appears to be combining two ends of the spectrum: programmable GPU for changing models and training, model-specific hardware for stable, high-volume inference. Nvidia is moving in a related direction by pairing GPUs with Groq-derived decode technology. The future may not be generalists defeating specialists, or specialists replacing generalists, and maybe a heterogeneous machine that assigns each phase of AI to a processor best suited to it. So here's the trade-off across the entire specialization ladder. What they change is the distance between a weight and the arithmetic that use it. D-matrix put a multiplier inside the memory. Etched wire the transformer shape into a circuit. Taalas makes the weights be the circuit. What the customer gains is efficiency per token on the workload the chip was built for, and independence from the memory bottleneck that constrains everyone else. What the customer gives up is flexibility. D-matrix still lets you swap models freely. Etched lets you swap any transformer. Taalas lets you swap nothing. Before we examine where that leaves the industry, there's one more attack, the one that questions the basic computation model beneath modern AI. Now we're moving into an area of computing, neuromorphic computing. The idea is this: your brain runs about 20 watts, a dim light bulb. On that budget, it recognizes faces, understands speech, plans, remembers, and learns continuously, all day, every day, without a cooling system. Now put that beside one of the racks we have been looking at, 120 kilowatts, 6,000 times the power budget of a human brain, and still unable to do plenty of things a 4-year-old finds effortless. That comparison is the entire reason this last approach exists. Everything we have examined so far, Nvidia, AMD, TPUs, Cerebras, Groq, D-matrix, Etched, Taalas, has been optimizing the same fundamental design. Move enormous arrays of numbers through arithmetic units on a clock continuously. The companies in this section are asking a more unsettling question. Not how do we do this faster, but is this the wrong way to compute in the first place? Because something in your head is doing it 6,000 times more cheaply. Every other approach in this video sits somewhere on the training prefill decode spectrum. This one sits off it. Neuromorphic chips are not competing for those jobs at all, which is exactly why they're interesting, and exactly why they belong at the end, rather than in the middle. So what does the brain do differently? 3 things, and each one maps onto something we have already discussed. First, almost nothing is running. At any given moment, the overwhelming majority of your neurons are silent. A neuron might fire a few times a second. Compare that to a chip, which computes every weight against every input on fixed clock. whether or not those numbers turn out to matter. Neuromorphic chips fire only when something changes. Point a conventional camera system at an empty hallway and process every pixel of every frame forever. But an event-driven system does almost nothing until someone walks in. Second, memory and computation are the same thing. Your synapses store the strings of connection and perform the computation on it. There's no memory chip, no bus, no fetching. You have heard that idea before in this video. It's what D-matrix is tracing when it builds multipliers into the memory array, and what Groq is tracing by refusing external memory. The specialization ladder we just climbed has been feeding its way towards something biology settled long ago. Third, there's no clock. Nothing in your head takes 2 billion times a second. Neurons act when enough input arrives. Energy gets spent on events, not on time passing. Put those together, and you get the 20 watts. Not because neurons are fast, but almost none of them are working at any moment. Nothing travels far, and nothing burns power waiting for a clock edge. And there's one more thing worth knowing. Neuromorphic isn't a single design. Some chips represent information as genuine time spikes, while others process events without temporal coding, trading biological realism for hardware that is far easier to program. So neuromorphic computing belongs in this story as a frontier, not as a current peer to Nvidia, AMD, TPUs, or Trainium. But its importance is conceptual, and it's the largest idea in this video. Every other company here accepted the model and optimized the hardware. The biggest efficiency gain available might come from the opposite direction, changing the model to suit better hardware, which is also quietly the risk hanging over Etched and Taalas. The further a chip specializes around today's architecture, the more it depends on today's architecture surviving. Now the 6 approaches we have just walked through all answer the same physical question. Where should the weights live, and how far should they travel? Each one gave a different answer. The next 3 companies matter, not because they answered that question differently. They matter because of how they have chosen to compete, and each one teaches something the architecture story can't. Tenstorrent attacks cost and control. Its processor uses an open RSCV foundation, an Ethernet-based mesh, and less expensive forms of external memory. It also licenses technology, rather than insisting that every customer buy a closed, vertically integrated system. Its 32-chip Galaxy system became generally available in April, starting around $110,000, and the company was last valued near $2.6 billion. The opportunity is openness. The challenge is building software and adoption against ecosystem with a long head start. Sambanova uses a reconfigurable data flow architecture and increasingly sell complete inference solutions, rather than asking enterprises to integrate accelerator cards themselves. It reached $1 billion in July, at $11 billion valuation, having precisely cut staff and pivoted away from training. Its story illustrates an important business lesson. Customers often want a working AI service, not an unusual processor they must learn to operate. Intel has the manufacturing history and engineering talent one might expect from a serious challenger, but its accelerator roadmap had repeatedly changed. Gaudi struggled to gain adoption, and it's being retired. The planned Falcon Shores product was cancelled, and the strategy has shifted to future rack scale and inference-focused parts. Intel demonstrated that resources alone don't create a stable platform. These companies matter, but they don't require separate theory of the chip war. They reinforce the existing ones, open versus closed ecosystems, product versus complete services, and the need for years of consistent execution. Before we go further, let's put every attack on one board. Across the top, the 6 approaches. Down the side, 6 questions. What job is this for? What application was it built for? And what does it change? What does it claim? What does the customer gain? And what does the customer give up? Take a moment with that. Every company we have met on one screen. And underneath, the role nobody else feels. Nvidia is the only entry on this board and doesn't have to choose. It isn't simply the strongest in any single cell. Cerebras is faster for one user. AMD carries more memory. Taalas produces more token per watt on one model. It's capable across all of them, and it comes with the software, the networking, the supply, and the distribution attached. Every challenger is better at something. Nvidia is adequate at everything. Every entry is a trade. Nobody found free performance. They found performance that caused flexibility or compatibility, and then bet that the thing they traded away wouldn't turn out to matter. And notice something about that row. Read it left to right, and it's almost the same sacrifice, made in escalating amounts. Cerebras give up memory capacity, Groq give up more of it. The matrix give up some model flexibility. Etched give up every architecture but one. Taalas give up everything except a single set of weights. There are not 6 different bets. There are one bet. The AI workloads have become predictable enough to stop paying for generality, placed at 6 different sizes. Some of those bets will be right, which raises a question I've been deferring, and it's the most important one in the video. Several of those approaches are genuinely, measurably better at something. So why does the scoreboard still look the way it does? Because designing a better architecture is only the beginning. A company chooses the architecture years before a customer can deploy it. The design has to be completed, fabricated, tested, and corrected. Then drivers, compilers, mathematical libraries have to mature. Servers must be built. Memory and packaging capacity must be reserved. Customer must test the system, rewrite or retune software, and decide whether they trust it in production. Only after surviving all of that does a clever chip become a business. And throughout that process, the target keeps moving. While startup is bringing up its first chip, Nvidia may release another generation, improve its networking, optimize its software, and change the economic of the comparison. A benchmark measures the architecture today. A customer buys a complete system several years later. The phrase AI chip encourages us to imagine one processor winning and all the others disappearing. But the evidence in this video points toward a different future. Training requires flexibility because researchers are still changing the recipe. Prefill reward enormous parallel mathematical throughput. Decode repeatedly read the model's weights and increasingly reward memory bandwidth, low latency, and predictable execution. A frequently used stable model may eventually justify dedicated silicon, while a new or rapidly changing model remains on programmable hardware. Those are different jobs. There's no reason the same processor must be best at all of them. This is heterogeneous computing, building one machine from processors designed for different parts of the workload. Nvidia's Rubin platform combines general-purpose Rubin GPUs with Groq-derived LPUs. The GPUs retain responsibility for flexible, memory-intensive work, including prefill and attention. The LPUs accelerate latency-sensitive portions of token generation. AMD is moving in the same general direction. It plans to integrate Taalas' specialized inference technology into system-level solutions alongside Instinct GPUs. A specialist does not have to replace every GPU. It can capture one valuable phase of an enormous workload. A decode processor can become important without ever training a model. Model-specific silicon can serve one popular model extraordinarily efficient, while GPUs handle everything that changes. Nvidia can therefore remain the largest platform while losing individual pieces of the workload, and its control of the complete system gives it a powerful defense. If a new architecture becomes important, Nvidia can partner with it, license it, acquire it, or build an equivalent function, and then decide where that function belongs beside the larger platform. The natural unit of competition is no longer the chip, it's the machine. The future may not belong to the best chip. It may belong to the best team of chips. The winner may be whichever company can assemble the best collection of processors, connect them efficiently, and make the entire system feel like one product. But even that picture leaves something out. None of these processors travel from an architecture drawing to a data center by itself. The design might come from Nvidia, AMD, Google, Amazon, or startup. The physical processor must still be fabricated. It needs high bandwidth memory, the compute dies, and memory stacks must be bonded together through advanced packaging. Network and silicon must connect processors, racks, and data centers. Every one of those layers is controlled by a relatively small group of suppliers. At the center sits TSMC, which fabricates most of the world's leading AI accelerators, the same companies that make the processor in your phone. High bandwidth memory comes primarily from SK Hynix, Samsung, and Micron. These are the same 3 companies that make the memory in your laptop and your phone, which is why this story has quietly reached consumers. When accelerator makers absorb the industry's memory output, prices rise for everyone else. Conventional DRAM price rose about 90% in a single quarter. Apple recently raised all of their products' pricing because of this reason. At least it is what they claim. Advanced packaging determines how closely the memory can sit beside the processor and how quickly data can move between them. This creates a second kind of competitive advantage, the ability to reserve scarce capacity. A startup can design an exceptional processor and still fail to ship it in a meaningful volume because it cannot obtain enough leading-edge wafers, HBM, or packaging. Nvidia's scale allows it to make enormous commitments, reserve supply years ahead, and give supplier confidence that the capacity will be used. Its advantage is therefore partly architectural, partly software, and partly logistical. The research firm SemiAnalysis recently revised its estimate of Google's Ironwood TPU shipments downward, from roughly 3.2 million units to 2.7 million, attributing the cut to difficulty ramping up capacity for the advanced packaging that bound compute dies to their memory stacks. Then there are Broadcom and Marvell, the custom chip manufacturers. Hyperscalers may understand their own workloads better than anyone else, but turning that knowledge into manufacturable silicon requires specialized intellectual property and engineering, memory interfaces, high-speed communication, physical design, packaging, and networking. Broadcom and Marvell help convert a cloud company's workload into a functional processor and system. That makes them the arms dealer of the custom silicon movement. Broadcom doesn't need one startup to defeat Nvidia. It can benefit whenever Nvidia's largest customer decides to build more of its own infrastructure. Broadcom reported $10.8 billion for AI semiconductor revenue in its second fiscal quarter, up 143% from the previous year, driven by custom accelerators and AI networking. It expected that figure to reach $16 billion in the following quarter. But those numbers also contain a warning. On June 4th of this year, Broadcom reported that 143% growth and the stock fell 12.6%, erasing an estimated $280 billion of market value in a single session. The reason was that guidance came in a few percent below consensus, and management didn't raise its long-term outlook. That's a risk across the entire supply layer. Stated as clearly as possible, these businesses are priced for a specific rate of acceleration. Growing at 143% isn't sufficient. You have to grow faster than the number in everyone's model. Value accumulates where capacity, knowledge, or distribution is scarce. The investment lesson is broader than any one supplier. Whether the accelerator is green, red, or designed inside a cloud provider, it still needs fabrication, memory, packaging, and networking. The visible chip winner is not necessarily the only company capturing the value. Now, trying to demonstrate another way the word win can mislead us. The usual comparison asks whether an individual Huawei accelerator is faster than Nvidia's latest GPU. But export restrictions and limited access to leading manufacturing, high bandwidth memory, and advanced packaging have pushed China toward a different objective, constructing a domestic ecosystem that is sufficient for its own market. A processor can lose the chip-to-chip comparison and still become strategically important if customers can obtain it, software support it, and enough of those processors can be connected into a working system. Huawei's approach illustrates the trade. Less capable individual processors can be combined through aggressive networking and system design to approach the aggregate output of more advanced systems on selected workloads. The bill arrives in power, complexity, and chip count. This is not a chip-level victory. It is a system-level workaround, and it reinforces the lesson from Google and Amazon. Strategic control and sufficient performance can matter more than winning the specification sheet. Chinese processors can displace Nvidia inside China without becoming the processor American cloud provider would choose. You do not need the world's best chip to build a domestic ecosystem. China may remain behind at the leading edge, while still becoming an enormous and economically meaningful AI chip market of its own. So can anyone actually beat Nvidia? On one workload, absolutely. Across the entire system, probably not anytime soon. We began with companies claiming to have built the fastest AI chip in the world. Now we can see why that sentence is almost meaningless without another question. Fastest at what? Cerebras can deliver extraordinary speed to one user. Groq created highly predictable token generation. AMD offers more memory and a second source for programmable accelerator. The matrix moves arithmetic into memory. Etched removes everything a transformer does not need. Taalas removes everything a particular model does not need. Neuromorphic chips question whether dense, continuously active computing is the correct foundation at all. Each can be better at something, because each gives something else up. Nvidia remained the most defensible, where flexibility, mature software, communication, and reliability all matter simultaneously, especially in training, frontier research, and rapidly changing workloads. It is more valuable where the workload becomes stable, repetitive, and enormous. Its largest customer can design processors around demand they already control. Specialists can capture individual phases such as decode. Open software can gradually reduce the cost of changing hardware. Domestic ecosystem can prioritize strategic control over peak performance. And supply chain companies can capture value regardless of whose accelerator wins. Nvidia can lose share without losing revenue, because the total market may expand faster than competitors take workloads away. And this is not defeat in the conventional sense, it's fragmentation. And notice what Nvidia is doing while that happens. It isn't defending the territory it has, it's opening new ones. Telecommunications networks, robotics, autonomous vehicles, scientific simulation. Nvidia keeps finding fresh categories of work that nobody else has run a specialized chip yet, because nobody knows yet what that work looks like. That turned out to be the shape of this entire industry, and it repeats. A new kind of AI work appears. Nobody knows what it will need, so everyone runs it on Nvidia, because the GPU will run anything. The work grows. It settles into a pattern, and once the pattern is stable enough to predict, somebody does the arithmetic and realizes a custom chip will do that one job for far more cheaply, so they build one. Nvidia loses that workload, and by then, it's already hosting the next unfamiliar thing. That's why the strategic question isn't which company has built a chip capable of replacing every Nvidia GPU. It's which workloads have become valuable and predictable enough that specialization creates an advantage large enough to justify switching. Nvidia's real position isn't that it wins at every workload permanently, it's that it hosts almost every workload first, and new ones keeps arriving. But the most likely outcome may not be one company replacing Nvidia. Nvidia won the last era by building the most complete machine around the bottlenecks that matter then. The winners of the next era will be whoever identified the bottlenecks that matters next, and build an entire business before the bottleneck move again. But the most likely outcome may not be one company replacing Nvidia. Nvidia won the last era because they built a complete system around the bottleneck that mattered then. The winners of the next era will be whoever identified the bottleneck that mattered next, and build an entire business before the bottleneck moves again. And if you'd like to watch new videos in advance, please consider joining the membership. Members can also propose research topics for the next videos. Research tier member can also download the infographics or presentation from my videos. Thank you so much for watching. I'll see you in the next one.